mentioned, the vector spaces we're concerned with in this class are Euclidean spaces. So our vectors are going to be in Vn. This is the book's notation. Some other books would say that our vectors are in Rn or in n space, but basically that just means that the components of our vectors are going to be real numbers, and a vector in V3 would be an ordered triple of real numbers that give me essentially the directions for getting from the tail of a vector to its tip. All right, anytime we have a vector space, we have two vector space operations. Those are addition and scalar multiplication. That's not to say those are the only things that we can do with our vectors, but those are the only two operations that are officially designated as vector space operations. We can, however, do something called subtraction. So if I have V and W, two vectors, in Vn, so that they're in the same space, I can define V minus W to simply be V plus the opposite of W. So it isn't really a new operation, it's just something I get by doing a combination of addition and scalar multiplication. Because of course, the opposite of W we saw is the same as just scaling W by a factor of -1. So let's suppose that I do have two vectors. Let's say we've got, here's our V and here's our W. And as long as I just have two vectors, I can think of these as being vectors in 2 space or in 3 space. If I've got two vectors in 3 space, I can translate them so that they've got their tail at the same place, and then I can see they lie in some plane. And I can just twist space to make that plane align with my whiteboard. Okay, so what does V minus W then look like? Well, if this is W, I'm going to go ahead and draw in the opposite of W, which would have the same magnitude and just the opposite direction. Then to accomplish V plus the opposite of W, I would take the opposite of W and I would translate that so that its tail is at the tip of V. And then the resultant vector, let's just get a new color for that. This vector right here is my V minus W. Okay. Now, anytime I want to illustrate V minus W, I can do it by simply doing this. Find -W, translate it so that its tail is at the tip of V, and add V and the opposite of W. Okay. But there is a nifty shortcut, okay? Because notice, right here, this was my V, here was my W, okay? If I were to draw in the same parallelogram that we had when we did our vector addition, where we translated W instead of -W with its tail at the tip of V, and then we had, of course, a translated version of V here, okay? So these two sides are W's, these two sides are V's. Take a look and notice this vector right here is a diagonal of this parallelogram. Looks to me like that's exactly the same as this vector down here. Does that actually work out? Are they the same? Yes, in fact they are. Because I can see that this vector right here, I get by taking V, and then the opposite of W would take me down to here. Okay. So what's kind of neat, if I draw the simplified picture again, if I just had V, and then I had W, without translating anything, if I draw them so that I've got V and W drawn like this with their tails in the same position, V minus W just points from the tip of W to the tip of V. It points from the tip of the one I'm subtracting, which is the W, to the tip of the one that I'm subtracting it from, which is the V. Now, it's often very easy to remember Oh yeah, V minus W, it just points from tip to tip. Easy to forget, does it point from the tip of W to the tip of V or vice versa? And of course, with subtraction, order matters, and with vectors, direction matters. You can always figure it out again by remembering this definition that it's the same as just adding the opposite of W. So if here's V, if I were to add the opposite of W, I'd be coming this way. So I can see V minus W has to be pointing right and up. Right and up would go from the tip of W to the tip of V, not vice versa. But that's sort of a nifty shortcut. If you also look then just at this part of the picture. Here's our parallelogram with two sides of V and two sides of W. That diagonal is V minus W. If I were to draw in the other diagonal, that's V plus W. Kind of neat. So that's how we can accomplish our subtraction. And of course, if we want to just do it algebraically, we would just do it component-wise. So let's write that out. Again, I'm going to write it out generically in 3 space. So let's let V be V1, V2, V3, be in the vector space of vectors in 3 space. Again, notice the vector has a bar over it. The components, which are just numbers, do not. We'll let W be W1, W2, W3. That's also in V3. And then V minus W, we just subtract like components. So it's V1 minus W1, V2 minus W2, V3 minus W3. Okay, so I understand what it looks like geometrically. I also understand how to accomplish it algebraically. Excellent.